So to run through the pipeline, I'll be using a set of simulated data. These were generated by ESA's Instrument Performance Simulator, or IPS, using an input scene that consists of a single point source with a spectrum taken from a template of an AGN at redshift Z of 1. This point source was then simulated in an observation that contained 4 dithered exposures using 4 of the cycling dither pattern positions. The instrument was configured with the G140H high resolution grading plus F100 long pass filter. The files that I've included that you can download for yourself, I've renamed and numbered for convenience according to the dither position. Just note that this is not the naming scheme that you would see for data that you in MAST. Those are more regularized naming scheme. It's a little bit harder to tell what's what, so I renamed that for convenience here. As with the pipeline, there are some caveats to be aware of with the simulation, some limitations in that. I won't go through all of these in detail. The main thing to note is that the simulator doesn't fully treat a lot of the throughput components that the pipeline, some of the pipeline steps correct for. So again, as with the pipeline stuff and limitations with the reference files, keep in mind that in particular flux information that you see here, again, is not necessarily reflective of what you'll see in real data in flight. So to start, we're going to start with the first cells to import some of the packages that we need in order to run the pipeline and look at the products. So I'm just going to shift-click through these and load these various modules, including some AstroPy packages and tools, matplotlib for plotting. And then the third cell actually loads all of the modules we need to run the pipelines in full and also individual steps for the Spec2 pipeline. Then we have some convenience functions and parameters. This cell here allows you to specify an output directory where the products generated by running the pipeline will be output to. So in this case, since it takes quite a long time for the pipeline to run through IFU data, there's a lot of pixels that it has to apply corrections to, and some of the steps, pretty flat field and Cubebuild can take quite a bit of time. We can't really do that in real time. So I've pre-computed all the products that the subsequent cells in the notebook would calculate. And I've put them in a shared directory that we'll grab from here. If you want to run through the pipeline on your own offline, simply comment out this line, uncomment out, add whatever directory you want to use locally to put the files. And then this is just a convenience plotting function. This cell here is a flag that you can set to turn on or off the actual running of the pipeline. So again, we don't want to do that in real time here. It can take several hours to run through this simulated data set through all of the steps. So I've set this flag to false so that all of the pipeline invocations won't actually be run. If you want to run this offline, simply change this to true. Just keep in mind, you may need to wait some time for some of the steps to run. All of the data, including the input simulation data and all of the pre-computed pipeline products, are available on Box. If you want to download those locally, simply comment out the first line of this cell, and this will download a zip file that's located on Box to your local directory, and then the next cell will unzip that, and you'll have access to all of the data products. So as I said, the inputs that we're using for these pipeline runs are a set of simulated data. It's a set of 4 exposures in a 4-point dither pattern. So just to give you a sense of what these input data looks like, we're going to take a look at one of the 4 exposures for the first dither position, indicated by D1 in the file name. In this case, because the simulations were using the high-resolution grading, spectra are dispersed onto both detectors. and each of those are contained on separate files. So this cell here will read in both of those files and then display the image that's contained in them. One of the limitations of the simulator is that, generally speaking, it doesn't produce a raw up-the-ramp data, so that we can't run stage one of the pipeline. It produces an electron rate map, which is the equivalent of the outputs from the stage one pipeline, or the level 2A data products, count rate images. And so we'll be starting our pipeline runs with the Spec2 pipeline for that. So these are essentially equivalent to the count rate images level 2A. So here's what the data looks like. As David showed you in his presentation, for NIRSpec IFU, we have an image slicer which re-images light from each of the 30 slices onto the detector. And what you're seeing here is light from all those 30 slices displayed here. Since the source is a point source here, what you're seeing is the PSF of that point source basically sliced up amongst the 3 slices. The actual position of the source is located within this slice here, where you see the counts are the highest, and then all the other slices are basically going further out in the PSF wings. The intrinsic spectrum that was used to generate the simulation, again, is a quasar emission line source, and you can actually see some of the emission lines here. Note characteristics of NIRSpec data with the gratings. There is a curvature of the spectral traces. The traces are not perfectly aligned with pixel rows. And also there is a wavelength tilt where the wavelengths are not perfectly aligned with pixel columns. And then the next image here shows you, again, the same exposure, but now for the NRS2 detector, showing you the long wavelength half of the exposure. Again, the curvature of the traces and some of the emission lines in the spectrum visible. So now let's move on and run through the pipeline. We'll start with Spec2. For this run, I'm going to be showing you how to use an association file to specify the input. Generally speaking, for the Spec2 pipeline, the association files are used when we need to associate other exposures that are needed for the calibration of a given science exposure. For example, if there are associated background exposures, such as in a nod set. We don't actually have that here because we're using a dither set where we don't do background subtraction. And so in this case, the association file simply contains the list of exposures that are to be processed. Here's what that looks like. So this association file contains all of the member exposures specified here. So we have a set of 4 dithered exposures, but 2 files per exposure with the 2 detectors for a total of 8 exposures that go into this. So the next cell actually will run the Spec2 pipeline if you set the flag to true. Here we've instanced the Spec2 pipeline. Here specified an output directory where the products will be saved. This also shows you an example of how to skip a step. In this case, we want to skip the flat field step because this is one of the limitations of the simulation. It doesn't treat all of the components that are corrected for by the flat field step, so we don't want to run that in this case. And so this will skip there. And then running this will go through all of the steps other than the skipped one for the Spec2 pipeline and generate products. So this next cell will actually loop through all of the 8 files, the 4 exposures, the 2 detectors, looping through all of the products that are generated by the Spec2 pipeline. The primary product in this case are the _cal.fits files. These are the 2D unrectified data, similar to what I showed you above, but with all of the various corrections actually applied to the data. These also would form the inputs into the Spec3 pipeline. As David mentioned, we also get from Spec2 a quick look product for each exposure, and in this case for each detector that includes an exposure level cube as well as an extracted 1D spectrum from each of those exposures. So this cell will loop through all of those products and show you some examples of what the data looks like. So just expand that. So here is a wavelength slice for for the exposure level cube for the first dither position on the NRS1 detector. So here you can see the cube is nicely reconstructed, the PSF of the point source, a nice peaked flux here, and you can see the extended wings and diffraction spikes of the point source there. And then here shows you the results from the 1D extraction done from this cube. Again, as David mentioned, for point sources, what happens is the pipeline will center a circular aperture at the position of the source and sum up all the flux at each output wavelength, resulting in this 1D spectrum like this. You can see the emission lines here in this source. And then here we see, for the same exposure, a slice of the output cube for the NRS2 detector, and then the 1D extracted spectrum from that. And then this just loops through the same thing for the other 3 exposures in this set. So that's the basic product for the full Spec 2 pipeline run. Now we'll go back and run through some of the individual steps of the Spec 2 pipeline just to give you a flavor for what those are actually doing to the data and what the intermediate products look like from those steps. So the first step here is assign WCS, and this step will actually compute for each of the pixels in the 2D spectrum various WCS world coordinate system values that are needed for subsequent steps, particularly for the cube building. That's primarily sky coordinates, RA and DEC values, as well as wavelength. For NIRSpec, this uses a fairly complex process, a large set of reference files that are computed using a parametric optical model of the instrument, which enables calculation of transforms between multiple image planes within the instrument and also out to the sky. So this cell would run that step here and output an intermediate product, which has a name with an appendix that has the name of the step in it, like this. And so we're going to take that product and load it into a data model. This doesn't actually do anything to the pixels of the data itself, but it computes all of the WCS information that can then be accessed subsequently via a WCS object. So after we load in the data model, we'll then get that WCS object in this cell. And the next here, this prints out all of the available frames for which you can get information, basically calculate the transforms between various frames. It's detector frame in pixel space to the slicer optical reference frame, and then also various frames on the sky. This next cell then shows you what the units of those different outputs would give you. So as I said, the main point of this is really to enable transformations for WCS values that are needed by subsequent steps. This next cell will show you one little trick of what you can actually use this for in 2D space if you want to look at information such as where the various wavelengths, for example, lines of interest, where those would be located in the 2D spectral space. So here we're going to look at a wavelength that corresponds to one of the emission lines in the spectrum, and then see where that's located in 2D space. So here we'll load in one of the slices, since these calculations for IFU data depend on the IFU slice. We'll pick one here, slice 4, or actually 3, because it goes from 0 to 29. We'll calculate a pixel grid, XY pixel values, and then feed that into the transform that enables calculation of world coordinates based on this input detector XY grid. And that ends up giving you values for RA, DEC, and wavelength corresponding to each of those pixels. And then we'll find which of those pixels is close to this wavelength value and then plot them on the 2D spectrum. And that's shown here in this next cell, where we're actually going to zoom in on the full 2D image just on a region of that particular slice. And the white line shows the locus of points that are at that wavelength value. And you can see here it corresponds nicely with this emission line in the spectrum like that. So that's just a little trick to enable you to look at the 2D data that may be of interest in some cases. So moving on, the next few steps we're not actually going to run. The background step here, if we had done a nod pattern, which would be most often used with a point source for the purposes of subtracting background, all of the other exposures in the nod set would be associated with each science exposure combined and then subtracted from that science exposure in this step. Since we're looking at a set of simulated data that were taken with the dither pattern, which does not optimize for background subtraction. And also this particular simulation set does not include background. We'll be skipping this step. Likewise, the next step is imprint correction. So as David mentioned in his presentation, the MSA shutters let through light that get dispersed onto the detectors in the same area where the IFU spectra get dispersed. The shutters, even though they're all closed for IFU exposures, they're not perfectly opaque, and a small amount of light is able to leak through. That leakage signal can be important in certain cases and be a source of noise, if not unwanted signal. And so in some cases that needs to be subtracted out. The normal methodology for that is to obtain a separate leakage exposure. And if those are obtained, the pipeline will, again, use an association to identify which exposures are the leakage corresponding to a given science exposure, and then we'll subtract them off in this step. Here, because we're using a simulation that doesn't actually include a leakage signal, we will skip that. The next step is source type. Here is where the pipeline attempts to determine whether the source that was observed is a point source or whether it's extended. This information is needed by subsequent pipeline steps. Some of the algorithms that are used are slightly different depending on which category. That is, it also affects the wavelength scale. So for IFU data, the pipeline determines this currently simply by looking at information that's passed from APT via the PPS database. When a user is designing the observations, when they first specify a source target, they have the option of determining, sorry, my dog is barking, of selecting whether the source is a point source or extended. If that selection was made, that information gets passed down to the pipeline and gets populated in a header keyword called the source TYAPT. The source type step looks at that keyword value and takes that to determine whether the source is point or extended. If that information wasn't done, or if it was marked as unknown, then for IFU data, the pipeline will default to extended. But here, since we've set this keyword to point because the simulations use a point source, we'll see here that the source type step populates this keyword as point, which is the result that we want. The next step is the flat field correction. So here, we're actually going to run this just to show you what this looks like, even though the simulation itself doesn't fully treat this. So for NIRSpec, this is a fairly complicated correction that includes 3 different components that treats several different areas of throughput. It treats a detector flat, which is the pixel-to-pixel response variations. There's a spectrographic flat, which corrects for throughput losses in the spectrographic stage of the instrument. And then an F flat, which corrects throughput from the 4 optics and filter wheel of the instrument, as well as the OTE. So what happens here is because all of these components depend on wavelength, the pipeline actually has to compute these corrections in real time for each exposure. And so what it does is goes through, looks at all the reference files for the 3 components, takes the wavelength per pixel that was calculated in the assigned WCS step, computes all of the correction values for each of those pixels, combines all of the three components together into a 2D image of the correction values, and then divides those into the science exposure to affect the correction. Here we're going to run this step, and there's an optional parameter to save that calculated flat, so that if you want to look at what the results are, you can do that by setting that flag. It's not done by default. And then here's what that calculated flat looks like. So here you can see all of the pixels that see light through each of the 30 IFU slices now have a correction value, the combined correction value that's shown here. And again, this gets divided into the science spectrum to affect the correction, the results of which are shown here. The next step is a path loss correction. For IFU, we need to correct for throughput losses as a result of diffraction losses that are caused because the grading wheel is slightly undersized with respect to the beam at the pupil plane of the grading wheel. Right now, this is one case where the reference files are all have all factors of unity, so there's no actual correction computed here. Because we can't measure these corrections until we get in flight and can observe standard stars. But here's an example of what would happen if you were to run that step and the results that are output from that. Next up is photom, which currently simply applies a scalar conversion factor, which converts the data, which up into this step are in terms of a corrected dn per second per pixel, and converts those to physical units. In this case, because we're looking at a point source, those units should be in megajanskis. And so here we'll just look at the output, and again, all this does really is populate two header keywords, which gives you that conversion factor in two different units. Now we finally come to Cubebuild. So now that we've made all of these throughput and radiometric calculations, calculated the WCS values for each pixel, all of that information now goes into the Cubebuild step, which rearranges everything to build a cube in a regularized grid in RA, DEC, and wavelength coordinates. And so we run that through here. And so again, this is at stage 2 for the Spec 2 pipeline. This is an exposure level cube, 1 cube per detector per exposure. And here shows one of the wavelength slices from that output cube, showing you similar results to what we saw from the full Spec 2 pipeline. And then extract 1D, again, this simply does aperture extraction from this exposure level cube. And here's the results of that, showing similar to what we saw above. You'll notice the spectral shape is a little bit different because in this case we have applied the flat field correction. Quick run of the Spec 3 pipeline. David will be going into this a little more detail using MIRI data as an example, but just to show you a simple example of how this works for NIRSpec data. As with the Spec 2 pipeline run, we'll be using an association file which contains a list of all of the cal.fits files, the basic output from the Spec 2 run. Those are all of the inputs that go in together. So at stage 3, we're combining all 4 exposures and also spectra on both detectors into one single combined cube. And here's where we invoke the Spec 3 pipeline. We'll be skipping one of the steps of Spec 3 is an outlier detection step. This is sort of an additional layer of attempting to identify any outlying pixels that weren't found in earlier steps, particularly in the stage 1 pipeline, such as cosmic rays. What happens here is basically that compares a stack of all the pixels in the output spaxel grid and tries to identify outliers from that stack based on noise information. We're going to skip that here because the input simulations don't include outliers. And there's still some tuning that needs to be done to get this to work properly for, especially for point sources. Right now, it tends to flag too many pixels. And then here's the output. So here are two different wavelength slices from this output cube. Here again, you can see a nice reconstruction of the source PSF. And then here is the 1D extracted spectrum from that combined cube, where you can see now the full wavelength range here for this particular grading setting. And then here you can also see the wavelength gap introduced because of the gap between the two detectors.